So welcome back again to this online course on advanced plasticity of solid continua. In the last lecture we have been discussing about the models for isotropic and kinematic hardening. Specifically we have been discussing about isotropic hardening and we have not yet completed it. So we will continue with the thermodynamics of isotropic hardening, especially the dissipation structure associated with it in this talk. So let us start with from wherever we left. Okay, so this is the dissipation structure slide, as you can see. So basic structure to understand the dissipation is to apply Coleman-Knoll. That is to remove all zero dissipation terms, right? Corresponding to the thermodynamic closure. Remember that sigma, for example, written as del psi E by del epsilon E, if you write this, that is a zero, that leads to a zero dissipation term, because you can clearly see that, right? We have already seen that. Now, so thermodynamic closure means arriving at these terms, right, and then removing those terms from the dissipation inequality that we arrive at after combining the first two laws. So if you do that, then the reduced dissipation inequality in this case will be simply this, right. So you have this the deviatoric stress inner product with epsilon p dot as the dissipation as if it is perfect plasticity minus the stored energy xh, which is the thermodynamic force acting on alpha dot, producing the work needed or energy, stored energy, right. So basically the plastic work, therefore if I call this as the plastic work, right, this is my plastic work, right. This, if I take this other term xh alpha to this side, then we see that the plastic work can be written as the actual dissipation which gets into the heating plus xh alpha dot, okay, which is the stored energy due to hardening. Now, just to recollect and to ensure that you understand hardening plasticity well, let us have a quick comparison of perfect plasticity versus hardening. So in perfect plasticity, all the plastic work was dissipated. There was no hardening to store things, right. So isotropic hardening, it is not the case. That means not all the plastic work is dissipated. Part of it is dissipated. That part which is dissipated is called that D, script D, right. That part is dissipated. The other part is stored in psi h. It is in principle recoverable, right, only in principle. So we can actually have a much better insight into the whole thing based on a convex analysis, which we will do soon, maybe starting the next lecture. But for now, let us understand this, that if I fix my hardening variable alpha, then I can define an yield set C alpha as a function of alpha, but alpha is fixed now, okay. Over this yield set, using this yield set, which we have not so far done, we have actually found this yield set C alpha already. But what we have not done is that there is a separate way of understanding this evolution of the plastic flow based on what is called a dissipation potential, right, phi. If you look at it from this angle, this will be part of that convex analysis. I am just giving you an idea of what it is. If you look at it from that angle, the advantage is that you do not have to solve a constrained optimization problem. the way that we have been discussing plasticity, we are constrained by the stresses being restricted to C alpha all the time. We really cannot have stresses going outside the set C alpha. If you go for convex analysis to do the same thing, automatically there will be energies that will be developed which will create a wall, automatic wall, so that this explicit accounting of these stresses to belong to C alpha need not be done. You understand? This extra energy that comes, which produces that huge wall on the boundary of the set C alpha, is called the dual of this dissipation potential. We call it by phi star. Okay. So, we will come to all these details. The point here to note is that before we come to those details is that we do not need a constrained optimization to solve the problem, right. But the structure for so let us come back to the hardening problem. The structure for the hardening problem is the same as perfect plasticity, the same yield stress. The only difference is that the yield stress now is a function of alpha, correct. So, the basic structure is the same. Now, we come to the other aspect of hardening, which we call as the kinematic hardening, all right. So, the other aspect is nothing but the translation of the center of the yield set, all right, as we have already mentioned in the last lecture. When this happens, when there is a translation of the center of the yield set itself, you can understand what will happen, that the center itself, so now the center is not at 0, but at some other stress, correct. So, what basically happens here is that if you plot again the stress strain in a rather schematic, if very inaccurate, but still it gives you some understanding, right. Stress strain plot as if it is a one dimensional setting. Then what actually happens is that this is the elastic part, you go here, right, and then there is this hardening that takes place, right. When you go back, right, so this should be my yield stress even on this side, right. I am just putting a cross here to note that this is the same as this, okay. Now, in isotropic hardening I should have come back all the way here and then the yielding should have happened. But in kinematic hardening what happens is that the yielding starts much earlier. That means some directional information has already taken over, right. So, this is what is called the Bauschinger effect. So, this is called the Bauschinger effect, right, and the reason why this happens is because of the translation of the yield set itself. So, in kinematic hardening therefore, the center gets translated from 0 to some stress A, the center of the yield, the center of the stress space, right. So, other than that, I mean everything is the same. So, that means now the set C, the set of all admissible stresses, will be all deviatoric stresses sigma 0 such that the norm of sigma 0 minus that yield minus that stress A is less than equal to sigma y, right. Now, this A has a special name, it is called the back stress. It is also a tensor because just the same kind of a tensor as sigma 0 is. That is why I could subtract from sigma 0 A. So, it is the back stress tensor. As you would understand that in kinematic hardening alone, the shape and size of C does not change, only the center moves, right. This is I will try to show it in schematically later. For the time being, let us come to the thermodynamics. So, or rather, is there a schematic? Yeah, let me show you the schematic so that I can skip this slide later on. So, basically this is my original yield set in blue, this is my original one, right. This was the original center, this is my new center, this is my new yield surface. You see the shape and size remain the same, that it has translated depending on the loading direction, right. So, you can think of this quantity which is basically some difference of two stresses. No, this stress is 0 here, correct. This stress is basically A, this is the stress A, no, back stress, right. So, you can think of this back stress as if it is something like a residual stress that has got developed. So, that now if you try to go backwards in the opposite direction of the loading that produced this back stress to begin with, then you will face some resistance. You have to first overcome that resistance and then move, okay. So, that is what basically led to the asymmetry in the loading unloading that we showed you, okay. So, now we come back to the thermodynamic framework. The free energy as before, as in the hardening case, will be split into two parts. One is the elastic part, which is a pure function of epsilon E. It is an approximation, but it works in the sense that if you do this and do another part psi k, which is the kinematic hardening part of the free energy, which is a function of only the back stress, if you do this, then you can show that it makes sense by actually testing it, your hypothesis against experiments, right. So, it has been tested and so this works, okay. So, therefore, psi E is the usual stored elastic energy, right, which is entirely recoverable automatically. Psi k stores the energy due to the internal stress fields. Basically, this is because of the back stress. The internal stress fields, by that I mean only the back stress, okay. Right. Let us apply the Coleman-Knoll once more. I would once more request you to actually do it step by step, so that you become very comfortable with the application of thermodynamic constraints and reducing the problem to a much simpler one by getting this reduced dissipation inequalities, okay. So, please do that. Now, the closure relations are as follows. So, basically as in the last case, always your sigma is the derivative of the free energy with respect to the epsilon E, which is the strain corresponding to the elastic part, the elastic strain. And now this XA, the new thermodynamic force due to kinematic hardening, conjugate to this back stress A, is the partial derivative of the free energy with respect to the back stress A, right. Now, if you actually write the whole thing, do the splitting epsilon equal to epsilon E plus epsilon P, write the whole thing means the dissipation inequality in its original form as you derive by combining the two laws of thermodynamics under isothermal conditions, and then apply the Coleman-Knoll. After the splitting and all that, then you will come to the reduced dissipation inequality. So, it is basically given by this, right. This sigma here again is basically sigma 0, because the other part of sigma, the pressure part, does not do any work. This part of the plastic work is stored via the A dot term here, okay. So, this here XH, XA is the corresponding thermodynamic force. So, basically this is a stored energy as before, like the hardening case. It is perfectly analogous. This is the total plastic work, and the remainder is dissipated into heat. Now, let us talk of some specific models for kinematic hardening. To start with, the linear kinematic hardening. Again, this has a problem. Any linear modeling has the difficulties that it does not care where you are in the stress space. It always goes on either increasing indefinitely or decreasing indefinitely. That problem will be there here too, and as we had that problem in the isotropic, the hardening case, but then that can be addressed by introducing nonlinearity, as you will see later on. So this linear kinematic hardening model is called the Prager model, where as usual the psi k, the kinematic hardening based free energy, is chosen as a quadratic of the back stress with a constant c, which is called the hardening modulus, right. Now back stress being basically a stress, so that is why the inner product. Okay. So then if I differentiate this psi k with respect to the back stress, psi k is a scalar, back stress is a tensor, so I get a tensor which is basically x a, the thermodynamic force. In this case it is a tensor, the same type as A itself, and it is given by 1 by C A. Okay, so C is a scalar hardening modulus greater than 0. Now this is what actually happens. I mean, even though we have already described this, so if you use this linear model, then this will go on increasing this way, and then it will be go on moving this way. It will never end, which is not right, because bodies, the bodies that we see, solid bodies, cannot take indefinite stresses, right. Anyway, so let us continue with this. Now that we are at a different center for the yield set, so let us define the effective stress based on that center. That means call that effective stress as S, which is sigma 0 minus A. Translate it appropriately. Okay. So now the yield function will be given by f of sigma 0 and a function of the back stress 2, which is the new translated stress sigma 0 minus A, norm of that minus sigma y. This is equal to 0, gives the yield requirement, the requirement for yielding. The general thing is that it is always less than equal to 0. Okay. Okay. It is always less than equal to 0. Equal to 0 means the yield surface itself. Now we need to talk of an evolution law for A, right. We have so far defined, you remember, psi k, which is basically the free energy associated with the kinematic hardening, but we have not yet defined how A moves, how A evolves. This evolution law, again as with isotropic hardening, we relate the evolution of A with plastic strain. Again note that this relationship is algebraic only in the rate space. This implies that it is not algebraic upon integration, right, because an integration is pending. So this is rate, this is dependent on the history, right. So this is the simplest classical Prager law for the evolution of the back stress, that is the same modulus for kinematic hardening, C appearing, times epsilon p dot, the plastic strain rate, the simplest one. Okay. So actually if C is equal to 1, then you get just A dot is nothing but the plastic strain rate, but that is not true. In general C is not 1. So, but the important thing here is to understand is that the model says that the back stress evolves in the same direction as the plastic flow. Okay. Let us do the dissipation check as we have been doing all the time. Okay. So compute the dissipation as before. So this is the dissipation which actually converts to heat finally, right, seen as temperature increase, temperature rise, transfer to the ambient temperature finally. Okay. So now this consists of the original plastic work here minus this part is nothing but XA, the hardening force, Frobenius inner product with A dot. A dot is the rate of back stress. Okay. Now let us substitute the Prager law for evolution of A, which is A dot equal to C times epsilon p dot. Put that here in this. Okay, then you get this in a very straightforward manner so far, right. But then sigma 0 minus A was basically the effective stress S. So, therefore, we have D is the effective stress inner product with epsilon P dot, exactly analogous to perfect plasticity once again, except that in perfect plasticity this was sigma y, this S was sigma y, right. Actually, this was basically modulus of sigma 0's maximum, which was sigma y, but in this case it is not, right. So, the stress is shifted now. As I said that the linear kinematic hardening has its own problem, because the hardening goes on happening indefinitely, increasing the back stress indefinitely. That is not how the energy will be stored indefinitely. Bodies cannot store infinite energy, right. So, therefore, there has to be a limit somewhere. So, the nonlinear kinematic hardening addresses that in some way. Okay. This is also called the Armstrong-Frederick hardening. So, the linear model had unlimited translation experimentally. Naturally, you expect, even without doing an experiment, you would expect that translation of the yield set must saturate somewhere, right. It should not happen indefinitely. It actually has been seen also. So, to account for nonlinear kinematic hardening, we need to have a new evolution for the back stress A. And this modified evolution for the back stress A is given here. Okay. So, you observe the terms carefully. You can think of this whole equation for A dot to be an ordinary differential equation for A given epsilon P dot, correct. So, you can see what is actually happening. This evolution, the first term is C times epsilon P dot, which is the same term as in the linear Prager law, right, for linear kinematic hardening. The other term is minus gamma A times norm of epsilon P dot. Gamma is a factor which is a scalar, a material parameter greater than 0. But this particular whole equation, if you now think of it to be an ordinary differential equation given epsilon P dot, then this is like a force. This leads to a fundamental solution of what nature? So, A will be e to the power minus gamma times modulus of epsilon P dot times T times A0, that is the starting value of A and things like that. So, this will always control. So, as epsilon P dot increases, this fundamental solution will damp out, will remove to 0 the whole thing, the evolution of A itself, right. So, so if you look from this angle, you can clearly see how exactly by introducing this term the saturation of the kinematic hardening takes place, right. So, this is therefore called the dynamic recovery term, the second term on the right hand side of the evolution of A. This produces the saturation of the back stress, as we have argued already, and therefore obviously a more realistic cyclic behavior, right. Cyclic behavior means in plasticity you always can unload, reload and create a hysteresis and things like that, right. So, therefore, the cyclic behavior is an important element of plasticity that has to be checked whether it is always there or not consistent with your model, right. Your model should be consistent with the cyclic behavior. So, the geometric interpretation for kinematic hardening, as we have already seen, that it preserves the yield surface radius, it only translates the center and produces the directional memory, which is very important. It is something like a residual stress that produces a directional memory, right. The isotropic hardening has no such directional memory. It expands isotropically uniformly in all directions. Now, in experiments you will typically see combined both the effects of kinematic hardening and isotropic hardening. correct? So the yield function there, the yield surface is given by this equation in combined hardening. So you have the back stress effect here, defining your effective stress S on the left hand side, the norm of that. That will be equal to, on the boundary of the yield set, will be equal to the modified yield stress due to isotropic hardening, which is sigma y plus R alpha. R alpha being the hardening rate, or XH. Remember, this was the hardening force due to isotropic hardening, right? So this is my combined hardening thing. This is how we define the set of admissible stresses in combined hardening, correct? So let us have the energetic interpretation of this kinematic hardening, at least, So basically what actually is happening, so basically you can, if you think of this sigma y as a function of the isotropic hardening alpha, so sigma y is a sigma y of alpha, then this can describe the combined hardening also, there is no problem, okay. So the moral of the story here is that this is my plastic work, this is the equivalent of stress power in plasticity, this is my stored energy due to the kinematic hardening aspect, and this is my dissipated thing, provided there is no isotropic hardening. If there is an isotropic hardening, then there is this alpha part and the corresponding thermodynamic force that will actually produce another storage part for energy, which will go inside into this and get added, okay. So that is the whole business here. So this is how the energy landscape behaves. But the difference is that the kinematic hardening stores directional energy and the dissipation remains associated with always the yield stress, because it gets subtracted, the back stress gets subtracted from sigma 0, and so the dissipation that actually happens is not because of hardening at all. Hardening cannot produce heating. Any heating that is actually happening is because of the perfect part of the plasticity, right. So that is an important point to remember. There is one aspect that I have already been touching on again and again, which is the convex analysis, without getting into the details, which we should now do. So in the next lecture, we will give you a fill of this convex analytic treatment of rate independent plasticity. As I have already said, that this is a very nice and scientifically elegant means of solving a plasticity problem, continuum plasticity problem, within the framework of unconstrained optimization, right. So we will start, the starting point for this will be the dissipation potential, and therefore the yield phenomena will appear as a result of the definition of the dissipation potential, right. So we will discuss this in great detail in the next lecture. Till then, goodbye. Thank you for your attention.